for the last year or so, which is really good fun. And I'm going to tell you a little bit about why West Antarctica is so critical to sea level rise, a little primer to get everyone on the same page about ice flow dynamics, and then a little bit of the results and things that I've been working on, which is quite fun. I know this is supposed to be a pretty general group that comes from a lot of different backgrounds, so I thought that was the best way to do this. But let's start it off with like the most important bit. What you're looking at right now is a NASA model of carbon emissions, and it's super high resolution. This came out last year. You may have seen it like floating around on some social media bits. It's really quite fantastic. We see all of these point source emissions as well as natural emitters coming out of greener areas. And something like this is really predictive and powerful because it allows us to kind of see what's actually going to be happening and forcings that we would expect to see in full climate scale integrated models with lots of multiple systems, carbon being very well linked with temperature, as I believe most of you should be familiar with. I don't know why they zoom in really big here. I wish I could play this at 1.5 speed, but stick with me just for a second. At least it's very pretty. Look at all those little point sources mapped. Now, what you can see here is huge diurnal cycles, day and night, where you'll get carbon emissions and sinks in green areas and huge industrialization going on, especially out of China. You see more of that diurnal cycle down here in Central Africa, and point source emissions coming out of Europe. And you can see tons of this swirling of where all those emissions are going and sort of the impacts of the different areas that they have. And yes, a lot of it is in the north, but the climate system is, of course, a little bit more complicated. But carbon is not, in fact, the only thing that is going to be a main driver in our system. We also have methane. Methane is really interesting because while it's still being measured, I think it's going to pop up here in a minute, for parts per billion. It's like much smaller concentrations. It is, I believe, it's like 200 times more potent of a greenhouse gas than CO2 for the first 25 years it's in the atmosphere. And there's a lot of naturally occurring sources out here in wetlands. We'll have a lot, you'll see that all throughout, like the Amazon rainforest, which is a significant proportion of it. But there are other sorts of point sources for it as well, especially with the advent of natural gas. Natural gas being very important result out from like fracking, et cetera, in the United States. Because natural gas is 90% more and more methane. Now, Europe's the only place that has stable or lowered concentrations of methane in the last 2 decades. You'll see that rice farming and livestock is a very big part of methane emissions in Asia. And over there, little bits coming out of oil refineries. And with massive industrialization booms coming out of China, yet again, you'll see lots more of these point sources emitting large amounts of methane that are very important drivers. Now we can kind of like counteract that with these like light sweeping bits that you'll get emitting out of the Canadian Arctic, sort of like small amounts of thaw and maybe permafrost. We could see some very large amounts of methane coming out of those if a large seep was broken or thawed at some point. And then of course in this, you see that there are diurnal cycles and then methane emitting out across the United States. Why is this important? Because we can look at changes from the global temperature mean, these are the anomalies from 1880. And as we start ramping up through industrialized times and wars and more industrialism and international globalism, you'll start seeing the effect of what the Earth system does, which is that it takes energy and it tries to balance it. And when it takes on all this excess heat that's generated from greenhouse gases and solar insolation, it tries to bring them to the poles. Right? This is the polar amplification effect. It's been recorded at ×3 or ×4 the amount of warming that you normally see on average over the rest of the globe. So with these large concentrations of warming in these places that are covered with ice, we clearly have a predicament where we see a amount of melting beginning, especially in these lower latitude regions, such as like southern Greenland or the Antarctic Peninsula. We know it's important because there used to be other ice sheets that we don't currently have anymore. So we have like the greater like Scandinavian ice sheet and the Laurentide over North America. And they contained about 110-ish meters, of sea level rise themselves and are no longer with us. So we had lots of coastal areas that may even have had civilizations at the time, but when they started retreating, like living people, not necessarily full-blown like cities or anything, they started retreating after the last glacial maximum about 25,000 years ago until they were gone about 12,000 years ago, we would see a very large amount of sea level rise. Now, we can do some quick and dirty GIS work to just kind of gain the idea of the extent of this. We lose all of the ice in Antarctica and Greenland, and we don't account for isostatic uplift, and we don't account for the thermal expansion of the ocean, which could actually be quite considerable. I think it's about 40% of total contribution so far. And we just map all of that directly onto the Earth's surface. Like, this is the places that would become inundated. And that's potentially important because if we map where the humans are, we see that with a estimate of 2025 global census mapped onto this, we're looking at a risk of about 1 billion people. But of course, all of this ice won't go away in 2025, and definitely not for hundreds and maybe thousands of years. So we would have, particularly speaking, a lot more people. But if we just take this quick and dirty estimate, we can just kind of see an idea of the risk levels that we might be worried about, particularly South Asia, the entire country of Bangladesh, lots of like industrialized China and Korea, all coastal cities all around India, and large parts of the island nations. If we want to bring it back home a little bit, we can look at Northern Europe, all the Low Countries, all of like the flatland of East Anglia, lots of stuff around the sea, and into the edge of France. For reference, there's that little dot is Cambridge, which would be just a nice place to build a pier, apparently. Now, what we really want to see, though, is like, what is the ice doing like right now? Like, how is it retreating? And so we can get a global kind of like big picture view by following along with the GRACE and GRACE follow-on observations. These are gravitational satellites. They fly over an area and they accelerate and decelerate relative to each other with changes of mass. So we can measure that change over time. So what you're seeing here is from a baseline of 2002, the ice water equivalent, losses or gains in different parts of Greenland and Antarctica. You'll notice that there is a large concentration of loss coming out of West Antarctica here. Of course, a lot of Greenland, marginal edge of Greenland as well, but Greenland is a lot lower latitude than Antarctica generally as a continent. And yes, there are some areas where you'll see growth as well, while total loss in Greenland is quite high and sustained pretty much everywhere. It's lower and also more uncertain in Antarctica, but you do see these small areas of growth, mostly concentrated though in East Antarctica, which is relatively stable. But this is our concerning part right here, and we'll get to the geometry and geography of the area in just a quick second. But what we see when we put in all the big models, this is from the Cryosphere and Sea Level Rise chapter of the AR6 from the IPCC, is that like we have a lot of different projections. I added this nice little line at 1 meter of sea level rise, where we can look at where we would be at the end of this century and see under these different emission scenarios and adaptation and mitigation scenarios where we might be. Of course, this one also shows some of the outlier events that are still in fact possible, but not inside of like the confidence band. So there's we're not doing great right now, and we look to be on this sort of path, but there is still a lot of possibilities and uncertainties moving forward. So let's familiarize ourselves with Antarctica really quick. There's 3 main regions. You have the East Antarctic ice sheet, this large old continental craton covered in about 3 kilometers of ice just about everywhere. The separating it from West Antarctic ice sheet is the Transantarctic Mountains. The West Antarctic ice sheet is like a younger bit of continent that is has like accumulated like orogenies from island chains, similar to how the Western United States was built geologically. It's got covered with ice, and it's like kind of a rift zone, so it has a lot of different sorts of geology going on than in East Antarctica. It's covered by about 2 to 3 kilometers of ice, most other places. And then the Antarctic Peninsula is up here, which is more mountainous and has lots more of like outlet style glaciers than big ice sheet style ones. And then of course you have the two large floating ice shelves. So if we want to look at the topography of West Antarctica, this area that's losing tons of ice, you can see this nice digital rendering from Thwaites BedMap 2 back in 2012. You can see the huge transantarctic mountains holding back the East Antarctic ice sheet, and it's a nice stable configuration up there. You see the mountainous peninsula, you see some of the volcanoes that are out here, and then this nice little bit of sloping ice off of either side of the ice divide. But what's really interesting is when we pull that ice away and we look at the bed. Similarly, from Thwaites BedMap 2, although we do have BedMap 3 as of a few months ago now, which is just a little higher resolution and stronger predictor of what our radar science data says the bed looks like. But what I really want to point out is that, yeah, we have these volcanoes. You can see the whole transantarctic range and the Ellsworth Mountains here. But you get these huge troughs that are all sinking downwards as you go from the ocean, the continental plate down towards the interior of the West Antarctic half of the continent. And that's particularly disconcerting because if we just pull the ice away and just map out where the ocean would be, you notice that West Antarctica is not so much part of the continent as it is a archipelago. Yeah, you can't really see from my scale here, but yes, the deepest parts of the big subglacial troughs located over here in this Amundsen Sea part of West Antarctica. And what that means is that you have a nice retrograde bed slope. So as you're moving away from the ocean front, you're going downhill, like it becomes it's like a negative slope going backwards in. And what this means is that there's the potential for what's called marine ice sheet instability. There's also marine ice cliff instability, which is slightly different. But as you go down a retrograde slope, more warm ocean water starts to touch the front of your ice, and that melts more of it, which causes it to retreat and speed up, and then it touches more, et cetera, into this positive feedback loop that causes sustained retreat and then collapse. Now, marine ice cliff instability is an interesting theory where basically as you start retreating, more exposed ice is above the flotation point, and it becomes so thick up there that it collapses out of its own strength instabilities, which then causes retreat and it reveals a larger cliff. And looking into that was one thing that the modeling side of the Thwaites project wanted to do. But let's look at the actual ice flow velocities, because we can basically track the difference between 2 pixels from space of ice as it moves and get velocities. And this is what Antarctica generally looks like, sans this gap where the uncertainties get sometimes a little bit high near the pole. The polar gap is a thing that happens. Our satellites orbit directly over like this, but the Earth's at a tilt, so sometimes they can't acquire all the data they need, and correlations are not good enough for like a full scientific product, but we can still see what's going on there. But you'll notice that like these red areas don't really show up very often. We're usually somewhere in the orange when we're at the periphery of all the outlet glaciers, except once again in that one critical spot of West Antarctica where we were losing mass, where the bed is the deepest below sea level, and now we're seeing velocities of around 5 kilometers per year at the front. So yes, as I mentioned, this is the Amundsen Sea sector of West Antarctica. It has Pine Island and Thwaites glaciers mostly dominate it, with some small ones connected nearby. And Thwaites, on the recorded record, I think it's since 1996, I believe it was, has accelerated from about 340 meters per year to 4,900 meters per year at the along the grounding line in the main trunk, which is very, very fast and very drastic of a change. If you always want to show to your friends where this area is, you follow the peninsula down, you go past the first big boop, that's a scientific term, and boom, that's the Amundsen Sea. So that's, you can always reference back to the critical location. This is just a quick animation. I forget who made it. I think someone at Bass might have made this one. We can zoom in on the topography of the area. Thwaites, Pine Islands, some of the small ones next to it, big floating ice shelf in front of Thwaites. That's very nice. Can I jump onto here and change it? Oh, I wanted to speed this up because it's a very slow animation. All right, it doesn't seem to want to do it. There's a nice little bit where all of this terrain goes away. There we go. And we can go to about here. Sorry, there we go. So if we pull the topography away, you can see those big subglacial troughs with ice flow modeled velocities moving over them, and get sort of an idea of where the speed ups are directly over these valleys, and that they are much, much deeper than what we see over here. So we have potential for ice sheet instability where we are losing mass and accelerating quite heavily. And then this is just going to throw some ice back over the top to make it look pretty. And that's the general idea of what you get here. So I was told that, yeah, because we are in a general sort of audience and looking at some of the previous talks, I thought I would do a quick primer on ice dynamics, like how ice moves. So just quickly to go on this, we're not going to go over a ton of maths or anything. Basically, we have Glen's flow law, and that is a constitutive relationship for viscous ice, and it tells us how strain rate here, let me get my laser pointer back. Strain rate relates to your deviatoric stress. And this is a little map from a laboratory experiment done down the street from me and here in Cambridge back in the 50s, where Glenn and also his friend Nye were able to map how they relate to each other. And notice that these are logarithmic scales. So this is a very non-linear exponential relationship. They basically have a nice fit into here that shows that our nice flow exponent should usually be somewhere around 3. That's what we normally do. But you also have this ice hardness parameter. It's very, very temperature dependent. Ice is about 1,000 times softer when you go from minus 55 degrees to 0 degrees. But there's other things that are important in there: grain size, structure. The way the ice crystals are oriented can change the hardness by a factor of up to 100. So there's a lot of kind of uncertainty about this because it's very hard to test that or measure that consistently at scale in situ. Okay, so great. We have stress and strain rate. What are those? So simply speaking, stress, we're looking at gravitational driving stress. If we have a nice simple slab of a thickness h at a nice slope alpha, you can break up your little components and you can basically get the driving weight of the ice, which is going to be rho, your density of your ice, gravitational constant, your thickness, and the gradient of the surface slope to figure out how much is going to be pushing you in the direction of that red arrow. That's important to kind of like build up the basis of what we're doing for stress. But hey, we need deviatoric stress. Well, this is going to look a lot, but don't worry. I just had a nephew born. He got a bunch of blocks that we all had to draw on. So I drew him a Cauchy stress tensor so he can grow up playing with that. The idea is that on each surface of a block, you have a type of stress acting on that plane in one of those 3 directions. And that defines out this nice matrix or tensor. This stress tensor, then you can subtract out the pressure along the center line, hence P. P is 1/3 of the sum of all of these, and then what you're left with is your deviatoric stress tensor. So that's the sort of thing we need to know: how ice is going to flow in multiple dimensions, and then apply that into Glen's flow law. Now, if we do that, this is based off of Eric Rignot's, I think it's 2012. It was like the first continent-wide ice velocity map from satellites. If this is based off of if we calculate velocities just from ice deformation. And you'll notice that like the interior along all these ice divides is relatively close together, but there's some big magnitudes, particularly around the edges and with the floating ice shelves that you don't see here. And we account for that with sliding because ice is notoriously slippery, right? So there are two main forms of sliding that we account for, of so-called like Weertman style, because it was coined by a guy named Weertman, and a Coulomb, which was not coined by a guy named Coulomb, which makes a lot of sense. This is all straight out of the Cuffey and Patterson Bible of Glaciology from 2010. Great book. If you're interested in more of this, that is the go-to. In Weertman sliding, the idea is that we're gonna have like a thin film of water and have ice sliding over hard bedrock, and it'll get around bumps in two ways. You'll have an enhanced stress from the pressure buildup, and therefore an enhanced creep deformation over the top of these bumps, but also you'll have regulation or regulation, I think is how the English pronounce it. Anyway, but you hit the pressure melting point on the upside of the rock, and then water flows around it and refreezes where you have the underpressure side, and then the latent heat exchange continues this cycle to move through there. And what you end up getting is that your velocity at the bed is equal to some constant, and your basal shear stress to a certain exponent. This is n is normally 3, so this would be a 4 over that, so basically to the square, and then you can always take the r out and subsume it into the constant, and that's what we'd call like our friction coefficient. The Coulomb style is interesting because it assumes that we actually have a whole series of bumps across the bed and then these cavities in between, because ice is viscous and it will flow over but not immediately collapse into there, and that allows for subglacial hydrology to develop. And that means that we're going to have ice overburden pressure, but also water pressure pushing back, which is what we call effective pressure, this variable n. And so what we end up getting is not an equation that gives us the basal velocity, but actually a function that gives us the basal traction, or like friction, basically, as a function of your basal velocity, your effective pressure, and a sort of this is the Eichen's bound. It's like a maximum steepening of the uphill slope. But the idea is that like inside of these cavity systems, you develop like water that can build up in between them, or it can supersaturate, or it can also develop into Nye or Rothsberger channels, kind of depending. We usually use R channels because the math is a lot simpler. I think this was from Verder 2013, or maybe it was Ian Hewitt's earlier paper. But yes, this is a more complicated, more effective generally, but you do have to know intrinsic information about effective pressure. However, there's one more thing to take into account, is that we also have the sediments at the bottom of a glacier can also deform. This is from, I double pasted that in there. Bolton and Jones, or Bolton and Hindmarsh, I can't remember off the top of my head, but like they did some measurements. They like crawled into some channels and mounted like sensors underneath these Icelandic glaciers inside of the sediments, came back, measured them, and they had displaced. So we actually do see deformation of the bed. A lot of modeling tests have shown in the last decade or two that a regularized Coulomb style slip law can account for both the soft beds and hard beds and matches data quite well. So we would really like to be able to use this, of course, requiring knowledge about effective pressure. Generally speaking, the last bit of this primer is that like we have a force balance to maintain. We would always like model a glacier as in steady state, but they're really not. So the friction holding back the driving stress at the bed would be like a localized control if it's if the traction is equal to or greater than the driving stress. That could keep it all in balance. But when it's not like that, when you have really slippery areas like through the center of an ice stream like Thwaites or Pine Island, you need to bring into the idea of like global controls to maintain force balance. Global just being like over your glacier system, not like the whole planet. But yeah, where the bed is very weak and there's low friction. So you get these reductions in basal traction, needs to be resisted elsewhere. Basically your total force needs to be balanced by your local and your global forces. So where could we get some more other like traction from? We can go to the sides, like the valley sides or the shear margins. We can get sticky spots like frozen areas or large bedrock protrusions. And then that will relate to the internal strength of the ice over the distance between those, and that prevents unphysical runaway sliding. But we need to talk about the biggest sticky spot of them all, which is that when your ice flows out into the ocean at a certain point, it will become thin enough that it will detach from the bed, the grounding zone or grounding line, and become a floating ice shelf. And those floating ice shelves can end up bumping into high points of topography and make pinning points and cause back stress that helps hold a glacier in, which we call buttressing. Okay, so primer over. Hope that was good. If we're all on the same page, I can throw you some details or answer questions later if you want. But let's go back to the Amundsen Sea. This is where we have all the loss. This is where we have the high velocities. This is where we're worried about ice sheet instability and maybe that causing destabilizing effects for the rest of the West Antarctic ice sheet waste here. But yeah, I'd shown you in one of those animations, like we had a nice ice shelf in front of Thwaites. Unfortunately, we have some unhappy news. This is a great animation from Adrian Luckman. I think it was actually published in maybe it was Doug Ben's paper, and it has since been updated to 2025. The idea here is that originally from data of 2014 to 2021, I think this goes 22. You can see from satellite images the slow breakup of the Thwaites eastern ice shelf. The north is that way. So the eastern ice shelf is on the top, and the western ice shelf has broken apart and is just this floating ice tongue. But you'll see that these huge cracks formed, and there's some shearing going on through here. And that if we leave this pinning point, basically the buttressing effects are going to disappear. And because of all of these reasons, the media kind of jumped on over the last decade as we started kind of realizing we needed to do something. And they latched onto this phrase, like the Doomsday Glacier, and like I hate this name. This is a really annoying name. I think it disproportionately goes to scare factor right away. It's like it's a seriously huge issue, but I think we should really stick with the original analogy that someone said, that it's the canary in the coal mine. It's not the Doomsday Glacier. It's our warning sign for what we should see. If this starts to go, then we have some really scary possible rapid retreats for sea level rise. So what we did is we got together, or I wasn't here at the time to do so, but in 2017, we launched the International Thwaites Glacier Collaboration. Please contact Rob Larder in the group chat if you want to know more, but we'll go over a few of the basics. He was one of the head PIs. Basically, we have a bunch of field teams in red that are each going to study a different part of Thwaites with a whole international science community, mostly funded through the United States and the UK, but also some collaborators in like Germany and Sweden and South Korea and elsewhere. And we're all going to look at one different physical process and try to figure out if we can constrain our knowledge of how much ice we're going to lose, how quickly, and when Thwaites may destabilize. We also have two purely modeling teams, Dominoes and Prophet here, looking at calving fronts, which we have not fully figured out yet, and Prophet, which was looking at basically the synthesis, like the simple synthesis model, of like all of Thwaites together, and then coordinated by the SEO and B Rob. Cool. So this is all the things that we wanted to look at over all of the different teams, right? So many different things going on. We have like over on the shear margin, we have AP-Res, GPS, seismics. We have Ghost doing a traverse to try to get like these 2D profiles of what's going on in the bed. And I'll get into some of these a little bit later, but like, look, all these things are deployed, multiple boats, helicopters, models, autonomous underwater vehicles, looking at ocean salinity changes, CDW, and like melting, reef freezing, so many different things that we wanted to look at. The problem is that it's in the middle of friggin' nowhere, right? Like, sure, there's Waste Divide Field Camp, but that's like a temporary set of wooden structures and a runway out in the middle of nowhere. And And so like we can supply it with the Bass Traverse that'll actually drive their way all the way up to try to get to us, to get all our supplies and our science equipment and research, or we can fly some vehicles into Waste Divide and then work from there, or deploy via Small Twin Otter out to our individual field sites. Or for those lucky enough to do the sexy looking science that's out on the front, you could also deploy by ship. But yes, trying to get out here is very difficult. As far as planet Earth is concerned, it's basically as remote gets. It's not like there's any automated weather stations, so getting data will be quite difficult. This is just a quick overview of kind of like each of these projects. So like GHC was using cosmogenic nuclides to basically tell when different rocks were and were not covered by ice. It's our best paleo ice sheet extent proxy that we have to date. Super fun. They weren't able to get their ice cores dug to measure rocks below at some of the mountains on either side of Thwaites and Pine Island, but they were able on a second season to jump around between some of the islands and look at total extent measurements. And while they found that like Thwaites was in a stable configuration for quite some time, where it's at now is definitely an unstable spot. Melt was working out on the ice shelf, among many other things. They famously deployed this like radio controlled or remote controlled ice fin probe that measures like temperature, salinity, but it also had cameras, and they were able to get down and get like the first ever visual image of the grounding line, which is super fun. Tarzan did some automated, I think it's Tarzan did these automated like submersible like views that went under the ice shelves. Thor ran around by boat mapping the entire sea floor and convections all in between at the front. Ghost got to do these big traverses where they were hauling around these cabooses, and they had Vibrosize machine to do like mobile seismic measurements, which was really fun. Yes, very cool stuff on there. I can't speak to a ton to all of those because I was on the time team. From the little info you see up here, time was working on the shear margin. If you remember, I was talking about force balance a minute ago in the little flow primer. One of those global controls that you have to account for is along these shear margins, and Thwaites' shear margin happens to be in a very weird spot. There's no topographic control on why it's there, or at least a very weak one. Like on this western front, there's like a volcano right there, butts right up to it. But we didn't know why it's over here, and so we had to go out to the deep field, far away from the ocean, where everything is flat to look at it. So what the heck is a shear zone, right? I think rocks really illustrate the best example. When you have forces compressing and moving like opposite directions of each other, those stresses need to be accommodated inside of strains, kind of like that Glenn's flow law we were talking about. But those strains tend to accommodate inside of these bands, and they create these very particular shapes of how the minerals want to orient themselves. And so you get softer ice through here, but you also get like a sticky resistance effect through the whole thing. And ice is just another mineral. It's a inorganic, naturally occurring solid with a defined crystal lattice. My undergrad geology professor would be unhappy that I can't remember the fifth one right now. But yes, ice is just a mineral, so it behaves in a very similar sort of way. So we can very much take what we know from geology to map over to glaciology. Now, ice really starts to speed up and cause these changes in, or these opposite magnitudes in direction, where it starts to slip, which means that we need to know what's going on at the bed to really understand what the effects are going to be on the total force balance of the glacier, and if that margin is going to move, which has an effect on what the total flow line velocity speed of the whole glacier is. So to do that, it's quite difficult, but we use geophysical instruments because we can't just go poke the bottom of a glacier. We're standing on top of like 3 kilometers worth of ice. So we use 3 primary methods. We use ice penetrating radar. And this basically, you put a transmitter and a receiver and you transmit energy and you ping it, and then it hits some sort of reflector, whether that's the bed or an interior ice layer, and reflects it back. you're able to stack a bunch of those pings together and put together an image of what's going on, not just at the bed, but inside of the ice. Quite cool. Can be quite time consuming, especially if you want a very detailed and accurate record of an area. We can also do seismics, which is the same sort of thing, but instead of sending an energy pulse, an electromagnetic energy pulse, we send a wave. Like we're going to send a pressure and a shear wave. You can do that from a like that vibra-sized truck that Ghost had, where it's going to shake the ground at an exact frequency, or you can use a controlled explosive, or you can wait for an earthquake or ice quake to happen, and then you can see how those waves are going to reflect through your media, and you can discern what is going on at the bed, which is quite fun. Math's a little heavy. And then we can also use geodesy, which is where we're going to use high precision GNSS, GPS for the layman, to basically map to like millimeter accuracy where things are and remeasure them to figure out where they move to, and then use physics to infer backwards over this. So time's biggest thing that we did was a gigantic 1,000 seismometer grid over the shear margin, and with a long 27-kilometer flow line for the 2D. What this allows us to do is get one big line of generally what's going on across the bed, but when you set up in a grid pattern like this, you're able to get like a full azimuthal resolution of what's going on in the bed and make a full 3D topography map. Seismics are also interesting because when I just took a seismology like fast course to try to catch up onto this. This is not my forte. I'm a modeler, right? It's either pressure or shear waves when they're moving through liquid cease to propagate. And so you can actually look back and try to figure out where pockets of concentrated water are, which is really quite important when working on here. We also set off 731 small controlled explosives to get all of that information done, which was quite fun. Here's like the safety detonation kit hooked up to 2 GNSS clocks timed down to the nanosecond with double safety charging and blasting wire that heads off. And we would go out, measured out to sub-centimeter accuracy, all of these points that we wanted to fire at, and then put the seismometers in as well. And then we would set off a small explosion, move on to the next one, work in teams of 3, and 3 teams of those to try to get that done over the course of about a month and a half, which was nice when it looked like this. The low light and everything was quite beautiful, but there are some days where you're just completely socked in, and especially when the wind is high, you're not allowed to shoot seismics because it creates too much noise on the background of the seismometers. Okay, so this is where I've shuffled multiple talks kind of together. When we wrapped up everything, we needed to figure out at the end of the Thwaites project over this last year or so, like what our main conclusions were. And while my team, Time, and Ghost simultaneously deployed just a couple of years ago, that wasn't enough time to process all of our data. So the data that we did have was synthesized into those, yes, simple models over the whole area. And they found that that marine ice cliff instability, not ice sheet instability, but the one where the cliffs get too tall, not because of the retrograde slope, that isn't likely to happen. Also, we found that these big outliers seem like they're probably also not going to happen. Less likely, as I believe the words that we used. So we still have some pretty big threat range in here of what our sea level rise is going to look like, and still potential to hit 1 meter of total sea level rise by 2100 in some of these rougher cases, because Thwaites has basically on that retrograde slope, there's a few pinning points along the way, a few spots of like higher topography. And the last one is, don't quote me on it, about 75 kilometers back from the current front. And once we pass that last pinning point, we'll start to see sustained and rapid retreat across the entire ice stream, which will then start to collapse at least that part of Wace. So really trying to constrain like how long do we have until that happens is really important, and if we could avoid it, that would be wonderful. Still, there's new findings coming out even along. This was a really fun one from Eric Rickneau just last year, where he was looking at INSAR measurements from space and detected like up to 12-ish kilometers of intrusion of seawater along with tides that actually comes in and kind of jacks, hydraulically jacks parts of Thwaites' bed, which means that seawater intrusions can get inside past pinning points as well. So that changes our whole effective pressure of what's going on underneath the bed, or underneath the glacier at the bed. And that we don't have just some grounding line, we have a whole grounding zone that we need to account for. So particularly interesting to make more difficult models that maybe couple some of these processes a little bit better. Like generally speaking, we will do like inversions for friction parameters and then kind of like assume a certain flotation percentage in certain areas. But what I really thought would be important is if we can take the whole hydrology of the Amundsen Sea sector and couple that to flow models. Ambitious because not a lot of people have been able to do it, but that would be the next step, is to figure out like, well, how much are we really going to influence that Coulomb slip law? Oh, I have to keep clicking this to get the animations to go. So this is the sort of work that I've been doing recently. It's still in prep, but we can look at about a 30 some odd year evolution of the effective pressure and the basically the water sheet thickness across Thwaites. We can look at how the water wants to flow. And when we use this whole catchment model, there is one very interesting thing that in previous studies, water would just route down through here because we're missing a key spot in this area that was at hydrostatic equilibrium. But in every single model I've run, there's a large amount of water piracy that takes what's going off from the Ellsworth Mountains into Pine Island rather than Thwaites, which I assume is why we see slightly high effective pressures at the front on Thwaites in this. But we also see like how subglacial channels slowly evolve over time. These are like more efficient routing systems that are going to pull water away and basically reduce the water pressure, so increase the effective pressure and make the glacier a little bit more sticky around them. And you see it's a very complicated network when you're starting to look at smaller and smaller channels, but they usually coincide with just a few main pathways when you start looking at about 10, 20 cubic feet per second through them. So that's like the cutting edge of what I'm working on there. You can see sort of all of this. Yeah, so this is super fun to look at like the entire hydrology of the area and what that means for dynamics. Maybe you see like these fun little channels filling up right along the edge of where the shear margin is, and that may be like part of the control system. But yeah, we'll see. That paper should be submitted probably in January, so keep an eye out. But we haven't really found everything we were looking for, even though it's been about 8 years. And yep, that's due to our friend right here that I hope you all remember lovingly. No. But also, you know, when working in Antarctica, you can run into this as a problem, because some days you just get out there and it does not agree with you. It's just not scienceable weather. Also, there's snow drifts, and you'll just catch a toe and just go face down, which is never fun. On top of the bad visibility. But yeah, that's fun. I always like showing that off. So yeah, the main takeaways is that West Antarctica, like Greenland, is at very high risk of ice loss and is undergoing sustained loss. The West Antarctic ice sheet, because of its geometry, could very well collapse and contributes heavily to uncertainty in sea level rise projections, at least for the next couple hundred years. Thwaites is totally the canary in the coal mine. It's possible we could have large amounts of sea level rise by 2100, huge impacts for populations, sandy beaches, and lots of our infrastructure. When Thwaites does retreat to about that 75-kilometer distance, it will start rapidly collapsing and destabilizing. West Antarctica, which I forgot to mention, holds a total of 3.3 meters of sea level rise, all on its own, not counting what's simultaneously happening in Greenland. So we want more time and funding to kind of like really pin down what these projections are looking like, or hopefully to somehow avert it from happening, because the cost of adapting to 1 meter of sea level rise by 2100 is a whole lot higher than adapting to like half a meter. Those implications kind of like continue spanning, and also not everywhere in the world gets that average sea level rise the same way. We are on a very bad climate path, and we rapidly need to decarbonize to stop these forcings. I don't think that means natural gas, because that's just going to emit methane, which is even stronger of a greenhouse gas whenever it seeps, for like 25 more years. So I don't think that's really the strongest plan that we should offer. Now, it may seem like I'm trying to lean into the idea here of geoengineering, but it costs way more, like orders of magnitude, multiple orders of magnitude more than science, and we really have no idea what it's going to do. Martin Seeger wrote a really nice overview paper, a year ago, that just got published, kind of just looking at how uncertain all of that is. And if you want to get into that, I would highly suggest you talk to him, or at least read his paper. And then, very unfortunately, I wouldn't count on my home country helping out in that effort for the next 4 more years. So while that is quite heavy and uncertain, I think it's best that we wrap it up and just show you pictures of penguins. And with that, thank you. How are we on time? Oh, yes. 8 minutes. Nice. All right.
Oh, wow. Yeah, that was great. I think that
Oh,
was
thanks.
I think that was one of the best like preamble overviews to sea level rise that I've heard.
Oh, thanks.
Mhm.
Yeah, it leans heavily on some of those NASA visualizations to start, though.
Yeah, yeah, no, it's really good. Yeah, I guess we're gonna start the Q&A. Someone already has their hand up. Go ahead. Okay. In that case, I'll start. So you talked a little bit about the fieldwork that you did, and you said that it was in the middle of nowhere and it's really hard to get to and tough conditions. Can you tell us a bit more about like how you got there, how long you were there for? Was there anything that surprised you?
Oh, yeah. So so it's difficult to get out there because you have a bunch of 70-year-old airplanes that you need to fly from one side of a continent to another, and if the check engine light comes on, or the weather's bad at one of those spots, they have to turn around. So you have to wait for clear weather windows and well-behaved mechanical conditions to get stuff flown out. So we went from McMurdo with about 50,000 kilos of equipment to Waste Divide. And then we got stuck in a storm at Waste Divide for about 3 weeks. And then we were finally able to fly out by Twin Otter. I think we did 20 deployments to get everything out to the field site. And then between good and bad weather, we were out there for, I think it was 29 days was the average for all of us. So that makes it like quite difficult. And the first thing you do is people had cached equipment there during previous years, and then it was covered under about 3 meters of snow that we had to dig out, while also setting up camp and preparing the science. So yeah, it's quite difficult and fickle. But then once you get into a good rhythm, you start putting in 14, 16-hour days and get as much done as you can. Yeah, it's just the flat white, so there's not like there's many distractions unless it's blizzarding. Yeah.
Yeah, I was interested. You talked a little bit about hydraulic jacking, and I wanted to ask: do you know if this hydraulic jacking approaches the pinning point? At what point does it get to the point of no return? Is it as soon as the warm water reaches the pinning point and it sort of detaches from the bed, or is it further along?
So what's interesting is like in that Rigno paper is that it varied with the tides, right? So you'll have lift up and then regrounding basically like every 12 hours. So until the main part of the ice mass gets over that ridge or retreats past it, I don't see that pinning point not being super influential. But what I do see is that with the intrusion of extra seawater, it's changing your hydraulic potential that's going on your near upstream side. And that means that you're going to have heavily accelerated rates and like less, you're going to have more pressure, more water pressure coming back in from the ocean and basically clogging up the hydraulic system into Thwaites.
There's a sort of gradual effect.
Yeah, like slow. It's not like every tide more and more water gets in, but it's just every tide water is getting in, and it's also warm, so it'll cause extra melting.
Okay, Luke is asking a question. Do you use any other data sets such as radar to validate seismic measurements?
Yeah. So my colleague Danny May was running AP-RES. It's like an autonomous phase sensitive radio echo sounder, so like an ice penetrating radar, but has variable frequencies. He was doing a bunch of measurements out there as well, so we were able to kind of collate all of the data together to really match out at high resolution what was going on in the bed, which is very nice.
I have another question. I wanted to ask, what's the biggest thing that we need to do to reduce sea level rise uncertainty from Thwaites? Is the main bottleneck like understanding subglacial hydrology, because that's what a lot of people are focusing on right now, or is it we need more data to improve our models, or is it like understanding the link between melt and climate change? What do you think?
So I think we have a pretty steady idea of melt and climate change, but like continued monitoring of the ocean processes in such a remote area is going to be relatively difficult. But that's I think the strongest driver of like the front retreat. If we want to look at velocities and speedups and how quickly that any instabilities will basically take effect, I would say, in my opinion, that like coupling different processes together, if we look about like feedbacks between ice flow and hydrology, or between ice flow and the thermal regime that we cannot measure, at least very well, and like maybe how all three of those cycle together, will kind of enlighten us a little bit more into constraining how the problem should actually be solved and be remodeled into the future. At the same time, introducing more processes and more variables makes models harder to validate and potentially less predictable and more uncertain. So there's little bits that you got to go either way to really answer the question you're trying to answer. So still more work, but I would say it goes through looking at different process bases and then trying to continue up monitoring and ideally find a way to get a thermal profile out of the glacier. But that's incredibly hard to do. Yeah.
Thanks. Does anybody else have a question? Okay.
Yeah.
In that case, thank you very much.
Thank you for having me.
I'm going to stop recording now.